Thank you.
Thanks.
I just want you to consider what the following statement means to you. In October of this year, the Intergovernmental Panel for Climate Change released a report stating that unless we act immediately, global warming will cause catastrophic damage to the climate of our world. My name is Paul Yuile, and I'm here representing Scotland. And my bubber's not working? What is? I'm an undergraduate engineer at the University of Strathclyde in Glasgow. And we're going to be considering this question through the eyes of an engineer today. How can engineers impact global warming? So to give you an idea of how we're going to tackle this topic today, first of all, I'm going to define what I mean when I say global warming. I think that's really important. We're then going to have a look at some limits that have been previously defined before picking one of them, the 1.5 degree limit, and looking at some steps as to how we could potentially work towards that limit. And that will probably form the majority of today's talk, is looking at engineering solutions as to how we can actually turn from policy into reality. So first of all, what is global warming? So this graph in front of you, on the vertical axis, you've got change in temperature. On the horizontal axis, you have change in time. And whenever we talk about global warming, we always attribute a number of degrees to it. We say, oh, we've had 2 degrees global warming, that sort of thing. And that's going to be referenced to something. And the period to which it's referenced is the average temperature between the years 1850 and 1900. That's defined as the pre-industrial reference period. So that's before the Industrial Revolution occurred. And since then, we've had the Industrial Revolution, of course. We've had 2 world wars and various other things that have contributed to global warming. And as you can see, from that point, we've had a gradual rise in temperature up to where we are today. Now, there's 2 graphs present here. We can talk through exactly what each of them means later on, but the important thing for you to understand now is that the red graph is known as the no change graph. So that's what happens, what's predicted to happen if we don't change what we're doing today. If we continue to produce emissions in the way that we are currently, we're predicted that by 2100, we could be up to +6 degrees since the pre-industrial period. The blue graph is the change today scenario. So that's saying that, okay, so today we actually have our peak in emissions, and from this point onwards we have a steady decline. And that seems to be leveling out towards a 2 degree target. So where is that 2 degree target coming from? Well, you may have heard of the Paris Agreement, which was signed off formally in 2016, a couple of years ago. And the premise of this agreement was that the majority of members of the United Nations got together, signed this agreement to say we want to limit global warming to 2 degrees Celsius this century. So by the year 2100, no more than 2 degrees. But we also have a push goal of 1.5 degrees. So it'd be ideal if we can manage to limit to just 1.5 degrees. Well, what does it mean? When they signed this agreement, they didn't actually know what the difference was between these 2 scenarios. So they asked the Intergovernmental Panel for Climate Change, who I quoted from at the start of this presentation, to produce a report. They said, what's the difference in these 2 scenarios? What are the outcomes? What do we need to aim for? And that's what was produced in October of this year. So it was called the SR15 report. And on the right-hand side of your screen here, we've got a summary of, it's an infographic that I've pulled from the BBC. And it's a summary of some of the differences between the 2 scenarios. So in the 1.5 degree world, we're predicted to have 10 centimetres less of a sea rise, which could mean that 10 million fewer people lose their homes to rising seas. We talk a lot about the melting of the ice caps, and they've put a number on this. They've said over the next couple of centuries, this could mean, the difference between these 2 scenarios could mean 2 million square kilometres is saved. And also, an Arctic sea ice-free summer could happen once per century in a 1.5 degree world. In a 2 degree world, it could be once per decade. So there's huge differences between 1.5 degrees and 2 degrees, and the outcome of the SR15 report was we need to focus on 1.5 degrees. And what's happening right now in Poland is that policymakers are actually discussing this report and saying, well, what do we make of this? But it was interesting at the time when this came out in October to see how it was portrayed in the news. So here's a couple of articles that I picked up. The Guardian, they said there's one key takeaway from last week's IPCC report: cut carbon pollution as much as possible, as fast as possible. Well, yes, excellent answer, but not really hugely helpful. I mean, what does that mean to me? That seems like a problem that's bigger than me. Breitbart, who took a completely different stance on things, they said the failing IPCC ramps up climate hysteria with new doom litany report. They clearly didn't agree with the premise on which the report was formed or any of the findings found within. The Wired, who are an online magazine, they essentially panicked. They said, we need massive change to avoid climate hell, and then went on to say more and more clickbaity things within the article. But one article that caught my eye was the BBC. They produced a number of different articles on the report, but this one in particular, 5 things we have learned from the IPCC report. And they went on to list 5 steps to 1.5, which were lifted directly from the summary for policymakers of the report. Now, again, this isn't hugely useful for you and me. These are all problems that seem bigger. But I'm an engineer. So I looked at this and I said, well, go on then, how? How are we actually going to achieve this? You're saying nice things here, but how? How are we going to go about this? And I split it up into subsections. So first of all, emissions. The first step that they listed, global emissions of CO2 need to decline by 45% from 2010 levels by 2030. And then finally, step number 5, we want global net zero emissions by 2050. So they both fall under emissions for me. In terms of energy, renewables are estimated to provide 85% of our global energy by 2050. And also coal is expected to reduce to close to zero. And finally, land usage. It's stated we need a huge amount of square meterage to actually produce energy crops to produce energy from. However, I'm not a land usage engineer. I don't really know anything about that side of things. So I picked up on a keyword in here, energy, and went, excellent. That relates back to energy. And as you can probably tell, I'm keenly interested in the energy sector. So I said, well, actually, the energy sector is one of the huge contributors to our emissions. So can't we tie that in too? So I said, right, emissions. It comes back to energy. So from my biased opinion, as somebody that's keenly interested in the energy industry, I said, I reckon this all comes back to energy. So what we're going to do today is go through goals 2 and 3 here and just have a look at how we could potentially work towards them in the UK specifically. So first of all, renewables, 85% by 2050. Shown on the graph on the screen here is a graph. It's the output of a brilliant website called Electric Insights, and I'd strongly recommend that you go away tonight and have a play about on this because it's great fun. You can pick any period of time, a day, a month, a year, in the past 9 years and see exactly how we supplied our demand with energy. So this is from October 2017 through to October 2018. And I've shown purely renewables on this graph. So at the bottom, you've got biomass, topped up by a little bit of hydropower, and then on top of that, you have wind power in blue and solar on top of that again. So from 2017 to 2018, October to October, our average renewable penetration was 28%. 28% of our electricity in the UK was renewably sourced. So I rolled the tool back as far as it would go, which is to 2009, and I did exactly the same test. I said, okay, so what did it look like in 2009? There's no measurable biomass on this graph. Interestingly, there's exactly the same amount of hydro, and we'll come back to that in a minute or two. There's some wind power and no measurable solar on this graph. So in 2009, 9 years ago, we had an average of 4% of our energy was sourced from renewable sources. So when I first started university a few years ago, a lecturer stood up on one of our very first lectures and said, whatever you do in your career from now on, keep it simple. Don't overcomplicate things, keep it simple. So here's me keeping it simple. I've plotted a graph. On the vertical axis, you have percentage of renewable generation, and on the horizontal axis, you have time. And we've plotted our known values here. So in 2009, we know we had 4% renewables in the UK. And in 2017, 28%. And from the title of the screen here, our goal is to get to 85% by 2050. So keep it simple. You can challenge me on this assumption later on, but what if we just extend that linear graph upwards? Where do we land? It's looking pretty good. 2036, we hit 85%, and we can actually continue on from that, and in 2041 be 100% renewable. Excellent, that is a whole 14 years ahead of schedule. So how are we going to achieve that then? The infographic on the screen now is produced by Dong Energy, who are now rebranded as Ørsted, and it shows the progression of wind turbines over time. So in 1991, on the far left of the screen, you have a 500 kilowatt wind turbine, and this had a diameter of 35 meters. Come through to 2016 now, we have an 8 megawatt turbine with blades that are longer than the length of a passenger jet. So there's been this huge increase in size and power output of our wind turbines. Is there a limit to that? We haven't met it yet. There's plans for 15, 20 megawatt turbines. When will we reach a mechanical limit? Well, I guess the key thing is we haven't yet. So we can continue to make our wind turbines bigger, better, as Dong suggests, bigger, cheaper, and greener. And we'll get more renewable penetration that way. How about this then? This is PV panels. So if you look on the left-hand side of your graph, this orange trend line is price. Since the 1970s through to the past couple of years, it's become 250 times cheaper to make power using solar panels. So you can have 250 times as much power for the same price, just based on how we've driven down price through technological advancement. At the same time, on the right-hand side of that screen is uptake. So once we reach the critical price somewhere in the early noughties, people start to say, well, actually, yeah, I can make valuable power from this. I can make money out of this, and started to install. So globally, we've got a trend upwards in installations and downwards in price. That could continue. It would be ideal if it did continue. So it's looking like we're going to be okay. We can make bigger, better wind turbines. We can drive down the price of solar panels, install more, solve the problem that way. We'll be at 100% in no time. But it leads me on to a bit of a question. So I obviously have a keen interest in renewables. Does anybody else in this room have a keen interest in renewables? Yeah. What can you tell me about a highly renewable grid, a heavily renewable grid? What happens when it's not sunny? Intermittent. Yeah, so how can we tackle the problem of intermittency? Storage, yeah. And that's not a new idea. It's been around for a wee while, since the 1890s, in fact. We've had pumped hydro. The idea with this is, whenever you have too much electricity, you pump water from the low reservoir up to the high reservoir, and when you need that energy, you release it from its store as electrical potential, gravitational potential energy, and run it back through a turbine, thus producing energy and exporting to the grid. And that's great. It's a great idea. It's fully renewable once it's installed. And I live in Glasgow, so just up the road from me, there's a great example of this on the banks of Loch Lomond. However, I took a walk around London this afternoon and I didn't see any. So there's an obvious problem here. You need a hill, you need lots of water and lots of space, which don't tend to be in areas of high demand. So you can't have this locally. And also, we've managed to generate more energy-dense storage methods, such as Tesla. So you may have heard of Tesla, Elon Musk's company. They're based in sunny California. You might be able to see where this is going. And they came up with the idea, okay, how about if during the day, when it's nice and sunny, you power your house using solar panels on the roof? Excellent idea. Any excess power you generate is pumped into this battery on the wall, nice big block of lithium ion. And then at night time, when it's no longer sunny and you need power, you can still pop the kettle on. You're just pulling power from the battery now instead of the solar panel. So there's this idea of localized storage becoming a thing. Tesla are probably more famous for cars, electric vehicles, which if you think about it, are just batteries on wheels. So it's not a new idea to say, well, can we actually use these batteries on wheels as forms of local grid storage? Can we pull power from them when they're plugged in and use them to overcome local demand-supply balance issues? We will come back to this. It's not an easy problem, because obviously there's the needs of the user of the car and the needs of the grid need to be balanced in that case. But we'll come back to this. So, from my point of view, renewables are estimated to provide up to 85% of global electricity by 2050. In the UK, I think we can get there by 2050. How about coal then? Coal's expected to reduce to close to zero. Now, what's really important for me to explain to you now is a concept known as grid inertia. So if you think about coal power stations, nuclear power stations, gas power stations, they're all essentially big boilers. What they do is they take in water, heat it up, produce steam, and they use that steam to turn these big turbines. And there's hundreds of these turbines all across the country, all spinning at the same effective frequency of 50 hertz, 50 times per second. And that's where we get our frequency, our grid frequency out of the wall, 50 hertz. This is really handy because these are so big and heavy and spinning so fast. If we have a sudden mismatch between supply and demand, then you can actually pull power from the spinning reserves, the kinetic energy of these spinning blades, slow down your spinning machine slightly, which also droops the frequency of the grid, and you can pull your power that way and provide your load. That's a short-term solution. And while that's happening, somebody at National Grid is having a panic and saying, okay, there's a droop in frequency. What we need to do here is we either need to shed some load or we need to get some new generation online. But they have time to do that, and that's important. It's known as grid inertia. Why am I telling you this? If we get rid of all of these, we don't have grid inertia. We have very low grid inertia. A renewable grid is inherently low inertia. Wind turbines, big spinning masses, yes, but they're normally converter connected, which means it's not useful inertia in terms of the grid. And batteries, if you think about it, there's no moving parts there. They're not useful. This is a problem that I'm actively working to solve as we speak. My master's project this year is a group project, and we are working to design electric vehicle chargers that behave as if they were a big, heavy spinning mass in the event of a grid fault, so we can provide a dump of reactive power into the grid and potentially support the grid during these events. That's a story for another day, though. The UK has pledged to remove all unmodified coal power plants by the year 2025, 7 years away. So what do they mean when they say unmodified? So this is a standard coal power plant. You've got coal coming in the left-hand side and electricity magically leaving the right-hand side. And the process that happens inside this coal power plant is you're burning the coal, obviously. And that's producing lots of gases, one of which is CO2, which, as we know, contributes to global warming, contributes to the greenhouse effect. So the idea is, what if, inside this coal power plant, when you're burning, you capture the CO2 that comes off the coal, you pipeline it away and pump it deep underground, and you store it permanently in porous rock. Then it's no longer entering the atmosphere, no longer contributing to global warming. Problem solved. This is the UK government's goal, to have this on every coal power plant that's still operating by 2025. Could that be a stepping stone towards 2050 zero coal? It'll be an expensive stepping stone, and it will need to be put in place along with renewable penetration and also storage. So then, 5 steps to 1.5. We've talked about these two, renewables and coal. We've alluded to emissions because the energy industry contributes strongly to our emissions in the UK here. So let's say we've talked about them too. Number 4, we can talk about later. So in my mind, a limit is absolutely necessary for global warming. We've seen through the Paris Climate Agreement that policymakers inherently agree. Have we seen action as a result of that? That's a debate for another day. But 2 degrees, as agreed in the Paris Agreement, might not be enough. We might need to work towards 1.5 degrees, as the IPCC report recommends, and as is being discussed in Poland as we speak. I've told you that from my point of view, I see energy as a huge factor. I think it's hugely important that we decarbonise our energy sector, and that will be through the deployment of renewables, of extra storage on the grid, and carbon capture and storage in tandem. But what I wanted to bring your attention to is the role of engineers. None of this will happen without us. We're so important. We need to be skilled engineers, motivated engineers, and empowered engineers. And if we don't have that, we can't solve any of these problems. So I just wanted to leave you with this graph. This is from the draft climate change proposal for the Scottish Government, and I want you to completely ignore the timeline. But I just want you to look at what's happening on this graph. So on the vertical axis, you've got megatons of carbon dioxide emissions. And as you can see, it tends to go negative. We can talk about why that happens later on. But the key from this graph is that as engineers, we live in a world where we have the potential to not only limit climate change, not only limit global warming, but potentially reverse it. And I strongly believe, it's our responsibility to act on that. Thank you for listening.